Okay, good morning. Let's see if I hope, can you all see the board and hear me fine? Can you just type in the chat if you can see everything, hear everything? Okay, good. All right. Okay, so what I was going to do today is just review a little bit of the labor supply model. Last time I finished it, but I think we covered a lot in the last class, so I'll just review a little bit because a few people had questions about it. And then we'll start, hopefully today, the last topic that we're going to cover in class, which is the topic of non-parametric estimation. Okay, so today I'll just kind of give a little bit of an introduction, and we'll look at like one of the non-parametric estimators, which is a histogram estimator. Okay, and well, let me just say a couple words about the midterm project. Oh, sorry, I have to not use that thing. It keeps falling off. So the midterm project, I put up some notes about midterm. Well, first of all, due dates, okay? So the last day of class, like for us, the last day of class is April 28th, but the last day of class for the university is April 29th, which is a Wednesday. Since our class meets Tuesday, Thursday, it's really April 28th. But for me, it's fine if you hand in both the midterm project and the last problem set on the last day. Okay, that would be fine. So the last problem set I uploaded to the webpage, and it's not very long, since we decided to do this midterm project instead. It's basically just trying out some things, using built-in software, so you don't have to do extensive programming for last problem set. And even like one of the questions asked you to use data of your choosing. So you could even use some of the data from the midterm project to do the last problem set, like question number 1, okay? So I tried to make it not too involved, so that it won't be too time consuming, okay? Because I want you all to work a lot on the midterm project, because that's gonna be 30% of the grade, okay? So that's, I hope you all are, focusing on that. And there were a few questions that came up about the data set mainly, like the distance measures are in terms of kilometers. I actually talked to Gabrielle, and she was going to add a little bit more to the description of the data, like what the different variables are. And then I also asked her to rescale. I mean, she had actually rescaled already the test score measures. So she made it on a scale of 0 with variance 1. But I asked her to keep the original scaling because I thought it's a little bit more intuitive when you work with the data. And in the original scaling, it had a mean of, the mean overall, the standardized mean over all the localities is 500. Okay, the mean in our data subsample is going to be a little bit different from 500. So, but for the data, it's going to have a mean 500 and a variance 100. So if you get I think it's variance. Actually, I have to check if it's variance or standard deviations. But if you get a number, like if you find an estimate like 20, that going to this type of school increases your test score by 20, that's 0.2 standard deviations. Okay, so that's how you would interpret the test score data. So when you look at the test score data, the mean should be close to around 500, and then the variance, I think it's the variance around 100. Okay, let's see, what other question was there? Oh yeah, and then there was a typo that the lag was grade 8, it's actually grade 6, but she's correcting that. So just make sure that you get the latest description of the data and also the latest version of the data, okay? And then I also put up this note on general form of Roy model. okay? And the generality is just, you know, the outcome model is the same. It's basically, you know, y1 and y0, that part's the same. The part that's different is that the switching equation, like whether you observe y1 or you observe y0, is just specified as a general equation. And these z's, there could be some elements in z that are not in x. Okay, they don't have to perfectly overlap. And this fits our situation in terms of modeling the school choice decision, because distance to schools is a variable that really belongs in the z, you know, because that would be a major factor when you're deciding what school to go to. But it probably does not belong in the x, because why should the distance you travel to school directly affect your outcome? I mean, maybe you're exhausted by the time you get to school or something, but you could come up with stories where it might, but anyhow, I wanted to, and remember, you can choose what you want to put in Z, what you want to put in X, you know, I'm leaving that up to you. I'm hoping that, you know, looking at your different studies, we can get a sense of like how sensitive estimates are to different model specifications, you know, and hopefully maybe we'll have time on the last day of class, you know, because we're not really too far behind, I don't think, considering that we missed a week. We're a little bit behind schedule, but not terribly. So hopefully we'll have a chance maybe to talk about, you know, maybe you all can talk a little bit about like, you know, what your major findings were, like even if it's just 5 minutes or something on the last class, you know, maybe we'll be able to discuss a little bit what your major conclusions were from the project. Okay, are there any questions about the midterm project? The due dates, everything handing in the last day is fine, like the problems and the midterm project. You know, I'm still trying to figure out exactly what to do about the final exam. Like one way that I know, one person gave a final over Zoom, you know, so everybody took the final, I guess, over Zoom with the video on, so that it was actually kind of proctored, the exam. So that's maybe an option we have, you know, if I want to take like a timed final, you know, otherwise I would have to do maybe a 24-hour final. I don't want to, I don't want it to be stressful, like working with the software, uploading the software, things like that. So, you know, it's possible we might just do it by email, that you can hand in your exam, just to make it easy, you know, so that you don't have to get used to new technology. Is the internet working okay? Because I keep getting these messages, my internet is unstable. So hopefully, I actually have 2 internet, not that stable. Okay, you know, I might be able to fix it, because it might pause for a second, but I have 2 internets at home, 2 internet connections. Let me put it on the other. Okay, this one might be better. Okay, because I have 2 internets, and okay, hopefully. Okay, so let's begin. I wanted to first just review a little bit the labor supply model, and then we'll discuss the new topic, which is going to be some things about non-parametric density and regression estimation. So it's kind of a very modern topic, you know, something that a lot of econometricians work on. But let's look now first at this labor supply model. So remember, in this model, we have the observed wage offer. Okay. Well, I remember the notation. The wage offer is xi beta plus epsilon I, right? And you only see the wage for people that decided to work. That's the selection problem. Okay, and then we also have a model for what makes a person decide to work, and that's that there's a reservation wage and you work. So DI equals 1. That means you work if your wage offer is greater than your reservation wage. Okay, that's the labor supply model. And so the key problem is that E of epsilon I given xi and given you decided to work is not equal to 0. Okay, like if we didn't only have data on workers, if we had data on everybody, then it would be equal to 0. So we're assuming like E of epsilon I given xi equals 0. But the problem is we don't observe W for everybody. We only observe W for workers. Typically you only see wages for people who decide to work. And that creates an endogeneity problem. So the selection problem is equivalent to an endogeneity problem, right? They're the same thing. And so there are different ways of solving endogeneity problems. You know, as we saw, instrumental variables was one approach. But what we've been covering lately is this control function method, right? So that's an alternative. So there's IV approaches and there's like a control function method for solving endogeneity bias problems. So the observed wage you can write as xi beta plus E of epsilon I given xi given di equals 1. Okay, so we're basically adding the bias term. Okay, and then we'll subtract off the bias term, the same term. Okay, and you can say this is like your new error term. And that new error term, by construction, because we have subtracted off the problem, it has conditional mean 0. So what I mean by that is just like E of eta I given xi given di equals 1 equals 0. So that's by construction. Okay, but this is the control function. We require this control function. Okay. And it's called a control function because I use it to control for selectivity bias. So if I put in this function, then I did away with my bias problem, basically. But the key is I have to find out what this is, okay? So E of epsilon I given xi, so di equals 1 means the wage offer exceeded the reservation wage. So I just put in what that means, you know? This is equivalent to saying di equals 1 because it carries the same information. That means di equals 1. Okay, and then you put all of the observable elements on one side, the unobservable elements on the other side. Okay, so this is xi beta minus zi gamma is greater than vi minus epsilon I. And then I can divide through, like to standardize this. And here I'll divide by sigma. This is a different sigma. This is sigma epsilon. Okay, and then I didn't write it up, but I'm assuming that epsilon and v are jointly normal. Okay, so I didn't write that assumption, but we're assuming joint normality. Okay, and so the sigma is going to be the square root of the variance of vi minus epsilon I. All right, and so we can actually drop this xi because we're assuming the joint distribution of epsilon v does not depend on the x by itself, you know? Because we're saying it's normal and it doesn't depend in some way on x. So that's why we're able to actually drop this xi. Okay, like it might look like magic sometimes, in the slides where it like disappears to, but I think I have to add a footnote or something, because that's the assumption that the joint density does not depend otherwise on X. Okay, and now we can use those formulas that we had for like the conditional mean of one normal random variable conditional on the truncation of another one. So these are the same formulas as in the Roy model. Okay, in some sense, this model might even be a little bit easier than the Roy model. Okay, so here we will get, so we need the covariance of epsilon I and vi minus epsilon I. So it's sigma epsilon v, okay, sigma epsilon v minus sigma epsilon squared divided by sigma, which is this sigma here, times, okay, E of vi minus epsilon I over sigma, given this truncation. Vi minus epsilon I over sigma is less than, that's like the CI, you know, that we had before. We can call this CI. Okay, this is the truncation. So it's sigma epsilon v minus sigma squared epsilon over sigma times, this is truncation from above. Okay, so there's going to be a minus sign because it's mean 0 without truncation. So if we truncate from above, it'll be mean less than 0. And then the thing that goes in this denominator is always this probability. Okay, so it's going to be cap phi ci. Okay, so this is the Mills ratio. This term here is what's called the Mills ratio. And a lot of textbooks call this lambda, like lambda CI. And this is the control function. And we don't need this because we can just estimate this is something that's fixed. So when we actually estimate the model, it's okay, see how it says require this control function. Now I'm going to put it in. Okay. I'm going to estimate the model like this, like alpha times lambda CI plus the error term. Okay. Actually, make sure this chat is on. Okay. All right. If you have any questions, if you put in the chat, I can also like let you have the audio, you know, so. All right. So this is the Mills ratio expression. Okay, so how do you get the CI? All right, so you see in order to form the control function, we need the CI. Do you remember how you get the CI? Because we know the lambda, because we know the normal PDF. This is the normal PDF divided by the CDF. So we know what those functions are, but we need CI. So CI is equal to xi beta minus zi gamma over sigma. Where is that going to come from? Yes, Antonio, you're right. So it's the Probit model. And so this method was proposed by Jim Heckman. This is actually one of the things he's famous for, you know, because he got the Nobel Prize in year 2000. And it was really for recognizing like problems caused by selection and coming up with methods to control for selectivity. And the method is called two-step estimator. Okay, step one, let's see. Okay, I can fit it in here. So step one is Probit. So you estimate a Probit model only using data on who's working and not using data on the W's. Okay, so only using information. We're assuming that for non-workers, you don't see W, but you do see X. Okay, so X would be like years of education, you know, whatever variables you thought affected the wage offer. We're assuming you see that, but you don't see the wage because they're not working. Okay. So probit model, you would obtain CI hat, and then you use that to CI, and then you use that to form Mills ratio, and then you run the regression of wages, the wage regression for workers. So for workers only, okay? And when I run the regression, you see I get beta by itself, right? So the regression, I'll get beta. So from the probit model, I get CI, but I get all these individual beta minus gamma over sigma. I mean, I'm going to use that to form CI, but I do get all these coefficients, okay? And there are three types of variables. There's variables only in X, only in Z, and then there's variables that overlap, like they're in both X and Z. So if I have a variable that's only in X, then from the probit model, I get beta over sigma, okay, if it only appears in X. If I have a variable that's only in Z, then from the probit model, I get gamma over sigma. And then if I have a variable that's in X and Z, then from just the probit model, I get beta minus gamma over sigma. Okay, so I get a lot from the probit model by itself, okay? But now when I go to the wage regression, I also get beta by itself, okay, without the sigma. So notice that if I have beta from here, and I have beta over sigma from the probit model, then I'm able to deduce what is sigma, okay? So it's a little bit detective work, like I was saying. You have to kind of get creative about how you're going to obtain all your coefficients. So I have beta by itself, then I go back to here, then I get sigma. Once I have sigma, I can get gamma, okay? I mean, I'll get maybe multiple estimates of sigma, because if I had multiple X's that are not in Z, each of those I'd have a beta over sigma. You know, so maybe I could get 2 or 3 estimates of sigma, but they're all consistent. So, so I could choose like any one of them or combine them, you know, whatever I wanted. Okay, so you can kind of back out, and then from this alpha is going to give me this. This is alpha. Okay, and as I was saying last time, I think is, so you can see if I have sigma from here, now I'm able to get this numerator, but actually separating this numerator is a little more tricky. I have to actually use the variance of wages in order to separate this numerator. Okay, so that's something that Hagman discusses in his article, but you know, I won't require that you know how to do that. Like, I mean, this is enough just to know how you can separate these things. And I mean, this is a problem of identification. Like, how do I identify these different coefficients? You know, like from here, we identify beta by itself. Then you go back to the probit model, you identify sigma. That lets you identify gamma, okay? So you see how you get a lot, right? And then from this coefficient, that would be alpha hat. I can get sigma minus the sigma epsilon squared, you know, but it actually turns out I can get everything. So, okay, and then last time at the end of class, I was trying to describe how we can use this model for policy analysis, okay? And I did a couple different policies, okay? So I don't want to like redo everything that we did, but I just want to make sure it's solid. You know, sometimes it helps, I think, to hear it again in a slightly different way, like it might make it easier to understand. That's why I just want to review a little bit. So let's do the last policy that I did, because I know a few people had questions about that, and that was, so we did 2 policies last time. Okay, how could we get multiple estimates of beta and sigma? I wonder, when we regress wages against XI, should we include all XI? Yes, Yeah, so when you do the wage regression, you include all the x's, and then you've got this, okay? So you'll get, I mean, the reason you include all the x's is because the Roy model tells you they should all be in there, you know? So all the x's should be in both places, like in the probit model. I mean, according to the probit model, there should also be z's. So there's some variables that affect your reservation wage that do not affect your outcomes. So one of the examples is like husband's wages. That could influence a woman's decision to work, but would not be in her wage offer. Okay, that was the example. Like Hegman's example was for women working, you know, but you can do these sorts of models not only for women working, because sometimes you might observe profitability of a firm only if the firm survives. So you have a select group of firms that survived. You know, so the selection problem is actually appears all over in economics. Like it's not just labor economics. It's just his example happened to be labor supply and women working. Okay, so I wonder when we regress, yeah, we do include all the x's. And the reason I'm saying you can get multiple estimates of sigma is, let's say I have two x's, like xi1 and xi2. Then from the probit model, I'll have beta 1 and beta 2. Okay, let's say I have two x's that are not in z. So I'll have beta 1 and beta 2. Now from this wage regression, this is the same beta, right? We derived it from the model. This beta is the same as this beta. You know, so from the wage regression, I have beta 1 and beta 2. And each of these betas could be used to get an estimate of sigma. That's why I'm saying you could actually get multiple estimates of sigma. Okay. You don't always need the multiple estimates. I mean, this is like how you can get all these things, but for certain questions, you may not need to separate everything. Okay. Let's see. Okay, if we have multiple estimates sigma, how do we aggregate? You know, I would say people normally don't aggregate. You could take the average, definitely, or you could take maybe a midpoint or something, because any of them would be good. In practice, I don't know. I mean, how people actually do this in practice. You know, to be honest, in practice, people use this built-in software a lot, so they don't program it themselves. And the software probably has some mechanism for aggregating it, but I'm not exactly sure what the software does. Like Stata has this procedure called Hackett, and it does this. So probably it uses some way of aggregating it to combine the estimates of sigma. Okay. All right, so let's look at just this last policy, which was a tax policy, because a few people had questions. Like when I had office hours on Monday, I would say a few people had questions. And I'm assuming that the government collects taxes like they do in the US, which is first you get your wages and then you pay your taxes. Okay, so what okay, so Omkar has a question. What if all the variables in X are already in Z, but there's some variables in Z, not in X? Well, in this case, you need a variable that's in X, but not in Z, actually, because you're going to get your beta. And to get sigma, see if all variables were in Z but not in X, then every X variable would be part of Z. And so then for all the X variables, I would only have beta minus gamma over sigma. So beta by itself would not be enough to separate out sigma, right? So you really need to have something in X that's not in Z. because you need something that the probit model gives you just beta over sigma, and then you can isolate sigma. Okay. All right, so let's just look at this example of how we would study the effects of attacks, okay? And last time I was talking about different evaluation methods, and I like to think of it as being two types of approaches. So one is ex post and one is ex ante. So ex post evaluation is that you have some policy and you look what happened, okay? So like, for example, there's a famous paper, it was from the 90s, you know, when Bill Clinton was president actually, but it was a New Jersey minimum wage study. Okay, this was Card and Kruger. So minimum wage study. So there actually have been a lot of papers citing this and redoing this, and you can get their data even. But what they observed was they had Pennsylvania and New Jersey, okay? And then they had employment levels without any increase in the minimum wage. Okay, and then in New Jersey, they had an increase in the minimum wage. Okay, so that would be like a treatment, the way they describe. Okay, so Pennsylvania, and what they do is they look at the change in employment in New Jersey. So Y0T or Y1T prime, which is like after the minimum wage change. Okay, New Jersey. And then they subtract off the change in employment that they observed in Pennsylvania. Okay, and they did this even around the boundary between New Jersey and Pennsylvania, you know, worried that overall the states are different, but maybe near the boundary, they'd be more similar. This approach is an ex post evaluation approach because you're viewing the minimum wage increase as a treatment. You observe the increase and then you just say, well, you know, what's the effect of the treatment? And you're kind of viewing Pennsylvania as a control. Like Pennsylvania is a control state. And notice that this approach is not really using models, you know, like this is more like viewing it as an experiment, kind of a quasi-random experiment that, and so it's based on a lot of assumptions, like Pennsylvania is a good control for New Jersey. You know, you have to assume nothing else happened in Pennsylvania that would have, you know, also changed employment. This was employment, like average employment. I think it was employment among like lower education workers that would be affected by minimum wage. And their study, the reason it was kind of famous is they did not find a big effect of the minimum wage. In fact, the effect was negative, like the employment went up slightly in New Jersey. So they concluded that an increase in the minimum wage, because New Jersey increased the minimum wage. So they concluded that the increase in the minimum wage does not like lower employment for low wage workers. Okay, and so that's one of the big concerns, because theoretically, you know, if you think about standard models, if you impose a minimum wage, you would get a decrease in employment for workers because firms would cut back. If you make workers more expensive, firms cut back. But empirically, it's a question, how much do they cut back? And they were finding almost not at all, okay? It was kind of hard for them to explain why their number was actually negative, you know? Because like monopsony, you can get a negative number, but in the end, they ended up concluding it was close to zero. But there were big debates about like the data set they used, then because they used a survey, they actually called fast food places and collected their own data. But then later people redid it with like tax data, like IRS data, and they found similar results. But they concluded that the number was close to zero. Okay, anyhow, so this is what I would call an ex post evaluation study. So you actually see the treatment and then you try to figure out what happened, okay? And they're similar for a lot of different policies. Like there's one with taxes too. EITC. So this is done by someone named, let's see, Isa. I forgot her co-author's name though, but it's Isa and somebody. I think she had a co-author. But it uses the same methodology, but the control and treatment groups are different. So the treated is like women with children, you know, because the EITC is much more generous for people who have, EITC is earned income tax credit. That's what it stands for. And it's basically a negative tax. So the government supplements your wage. So, and this is for low wage workers who work a lot of hours. The government actually supplements their wage through this program. A lot of economists like this program. They think it's an effective way to transfer money to lower income people. But her treatment group was women with children because they get much more generous benefits. And her control group was like women without children. So without children. Okay. But that's also, you know, an ex post study because you're assuming you see a group that got treated. What I'm talking about, like in terms of using this model, like this treatment effects approach does not really make use of models, as you can see. It's more of a before-after comparison for a treatment group and a control group. So this general approach is called diff and diff, because it's a difference in differences. You're comparing this difference to this difference. So it's called difference in differences. You might come across, it's used a lot, actually. There are like thousands of studies, I would say, that kind of use this type of approach. But this approach cannot be used to analyze policies that have not been implemented yet. Okay, you have to implement the policy to see the treated, you know? So this labor supply model, if you adopt more of, you know, what's called a structural approach, where you impose more structure on the problem, you know, about how labor supply, the choices are being made. Usually it starts with the utility function and the constraints, and you derive out the model of labor supply. So within that framework, you can actually do ex-ante evaluation. And that means you can forecast the effect of policies that have not yet been implemented, you know? So that's very useful, like for the government to do before they implement a policy. Because say the earned income tax credit, there's a specific tax schedule, you know, and before you actually put it in place, you'd like to know what would the effects be if I put the tax at this level versus some other level, you know? So that's what I work on a lot is ex ante evaluation. I think it's more challenging than ex post. You know, ex post is pretty straightforward, but trying to do ex ante evaluation, you know, you really have to have a model that allows it. And then there's, of course, a question like, what's the best model? You know, so people have been trying to study that, like for different types of questions, what's a good model? So let's look at imposing a tax. Okay, and that's, or a tax. Okay, so I'm going to assume the tax is going to be 1 minus tau times W. So the wage you get to keep is tau times W. Okay, so the probability you're going to work, given your X and your Z's, is the probability. So now when you're considering should I work or not, you think about your take-home pay, okay, after the tax. So it's going to be tau, because you only get to keep tau. So tau might be like 90%. So for 10% tax, tau would be 0.9. Like you get to keep 0.9 of your wage, okay? And so that's going to be tau times xi beta minus zi gamma is greater than vi minus tau times epsilon I. Okay, and this sigma star is now square root of the variance of VI minus tau times epsilon I. Okay, so it's a little bit different from the sigma we had before, but all the ingredients that are in here, you know, it would be like sigma squared V plus tau squared sigma squared epsilon minus 2 tau sigma epsilon V. Okay. So if I had it, so suppose I estimated my labor supply model when there was no tax. And now I want to forecast what's the effect of this tax. Well, I can use the models because I'm assuming I have estimates of beta hat, sigma hat, tau. I can form this as well, or this sigma star, because I have estimates of these things. I mean, you can see how I actually need everything to do this policy. This is called a counterfactual policy because we do not actually observe it in the data. So you're trying to predict the effect of this policy. So I need all these ingredients in order to get sigma star, okay? But I can actually figure out what this is. And so this would be, you know, cap phi, and that tells you how the tax would affect the proportion of people who work. Okay, so basically I'm using all my model parameter estimates that I estimated without the tax, and then I could consider different levels of tau. Like I could do like a 2% tax, a 5% tax, you know, 10% tax. I can go through a whole range of tau and look at how labor supply would respond as I vary tau. Okay. I can also look at wages, okay? And that's, I think this is where we ended last time. I was trying to show how to look at wages. So this wage would be the wage before taxes, okay? So now DI equals 1, the group that chooses to work is going to be different, okay? So the wage that, and this is the wage that like the firm gives them before taxes are deducted. Okay, now people had some questions why this wasn't multiplied by tau, but I was thinking the firm gives you your wage and then you pay taxes. Okay, so this would be like the wage that you'd observe. This is the, so the crucial thing is the DI equals 1 now has changed, the group of people that chooses to work, okay? And basically the CI changes, like everything else is the same, it's just that CI tau, okay, it's a different cutoff value here. Okay, so I can predict now the wages of the people that choose to work. And the subsample that chooses to work has changed. You know, so like if the government imposes, let's say the government announced they're imposing a 10% tax. Okay, so probably we'll have taxes going up or something given all the budgetary problems from this virus. You know, they're paying all these unemployment benefits and helping firms. Like I imagine somebody will have to pay for this eventually, and we'll probably see some higher taxes. So if the government now says, let's say tau, it's going to be 0.9. So we can figure out what proportion will work. And then we can also figure out what will the wages be for workers. And knowing these things, you can actually figure out what will government tax revenue be. Like if you know the total population, I mean, this is conditional on I, so to get some overall average for the whole population, you'd have to average over individuals. But you can figure out what will their wages be, and then the government is going to get tau, or 1 minus tau times the wages, like times the average wages. Okay. So the model is actually very powerful because you can analyze policies that have not been put in place yet. Okay, so, and you cannot do this sort of analysis without structure. Okay, so that's why these are called like structural modeling methods, but you need to have the structure because you cannot do this with like a treatment effects approach. Because a treatment effect approach requires that you observe the treated. Okay, so that's, so it's kind of a limitation. All right, and of course, if the government then imposes the tax and later on you observe data where they actually have the tax, you could compare the actual results of what happened to your model's predictions, you know, and you can see how close they were. So that's what people have been doing, like exercises like that, where they forecast the effect of some policy, and then they later compare to the actual policy, see how close it is, their forecast to what happened. Okay, so I even have some papers like doing that type of analysis. Okay, so that was a bit of a lengthy review, but I just want to make sure, you know, that we didn't cover it too fast, that it's understandable. Does anybody have any questions about like how you could do? The other policy that we did last time was the tax one is more complicated because the sigma changes. So I kind of did the harder one. The other one was a simple wage subsidy where you just add an amount. Okay, and the other thing to notice is that tau, you could do this whole tau being individual specific. So if you had like an earned income tax credit that was targeted at certain people, and let's say mothers with children got different amounts from mothers without children, you could do that. You know, like you could allow tau to differ by individuals. Okay. Any questions or comments or anything about this model? Or about like ex ante valuation? I hope the distinction is clear. And the economists in the Congressional Budget Office do this kind of work. Oh, is there a multinomial variant of this analysis? Well, you know, I have not seen a model where they're choosing between different occupations. You could do it. You know, you could do like a Roy model, then impose taxes. Yeah, I mean, that would be an interesting model. Like you have a Roy model and then you impose taxes, and it would have implications for occupational choice, actually. Because let's say a certain occupation paid a really high wage, and then if you impose taxes or even like a progressive tax schedule, then you might induce people to choose different occupations. I mean, definitely. I mean, countries that have super high taxes at the high end are especially the Nordic countries like Sweden, Norway, Denmark. You know, their taxes at the high end are like 70%. You know, our taxes, our highest tax bracket, I think is, well, Trump lowered it. I think it used to be like 37%, and I think now it's more like 35%, but ours are at the highest, our highest tax bracket is pretty low compared to other countries. So, and probably, you know, having a tax rate of 70% at the higher end probably does induce changes in occupational choices. You know, all right, and then the Nordic countries, they subsidize at the lower end. Like if you lose your job, then they'll pay you 80% of your formal wage. You know, so it's like both ways. They tax a lot at the upper end and subsidize at the lower end. Yeah. Oh, so Omkar is asking about how accurate have the ex ante evaluations been. Well, I mean, I have a few papers. I would say in the examples that I've done, you know, they've been pretty good. I've been like forecasting effects of conditional cash transfer programs where they pay families to send their kids to school. It differs somewhat by the type of program people are studying. Like people have studied like welfare programs. Sometimes they give, let's say people on welfare, they might give them a bonus to find a job. Like they did that in Canada. They give them like $1,000 bonus to find a job. And then they used an ex-ante evaluation to predict the effects. They also did like, in the US, mandatory retirement is illegal, but a lot of companies give bonuses to retire by a certain age. So there's one paper that evaluates this type of like forecast of this bonus and then sees how it compares to what actually happened. So it's a small literature actually that does this. There are not that many studies. I guess Esther Duflo, she was one of the Nobel Prize recipients last fall, but she has a paper that they estimate the model in a treatment group that got, it's a group where the teachers got a subsidy, it was teachers in India, and they paid them a subsidy to show up to class because I guess they have a problem with the teachers not coming to class. And this is actually a common problem because I have a friend from Brazil and he said they also have this problem that, you know, teacher absenteeism. So they paid a bonus if the teacher came to class a certain fraction of the days. So they estimate a model where the teachers are deciding to attend class, and then they use the model to predict the behavior of the control group, you know, and they take away the bonus, you know, and they find the model performs pretty well. So I would say, you know, overall it's encouraging that modeling can be used to do ex-ante evaluation. But it's really the only way of doing it because you can't really, there's no other approach. It's not like there's a competitor. Like either you have to say, I can't do it at all, you know, or else you have to use some modeling. They do it in transportation analysis. You know, I think I mentioned that like in Paris, they're building a big subway system. You know, it's a very expensive project. I think it's 30 billion euros. Like that's how expensive it is. And so they analyze like where they should put the subway, you know, and they have models of transportation choices. They do the same for highways, you know, all different things. And then also models of like, at what price should they set the metro ticket? You know, because people's decisions to take the metro are going to depend on the price, you know, price of the ticket. So, okay, so those are just some examples of like ex-ante versus ex-post evaluation. It's actually closely related to the research I do because I do a lot of work on like ex-ante evaluation. I've also done like ex-post evaluation stuff, but a lot of people do ex-post evaluation. Not that many do ex-ante. I mean, with the virus stuff, you know, they keep coming out with forecasts of what the transmission will be and everything. And I think the models that they're currently using for the forecasts are done by epidemiologists, you know. So epidemiologists, they have models similar to economics, but in those models, people usually just kind of, you know, you can have a model where people randomly bump into each other, you know. So if you're modeling the transmission of a disease, you start with some model and then you can have people just randomly bump into each other. And if a positive person bumps into a negative person, that person becomes positive, you know, so you have some probability that it gets transmitted. But so it's similar to like the models that economists would do, but they don't have that much like individual choice. You know, like in our models, we model more the decision making of the individual. You know, so they're forming all these predictions, and then of course you see in the news sometimes the predictions, I mean, luckily they haven't been accurate in a good way, because apparently they predicted more fatalities than we've had. So so that's, I mean, it's still, to me, it's a staggering number, but they're in the news saying, oh, the predictions are not that accurate, but it hasn't been as bad as we expected. You know, probably those models could be improved if you had, like, if you knew individual demographics, you could actually put in like if you knew how different types of people would meet, and if you knew how different types of people take precautions, you know, like for example, people who have a job that requires them to work right now, you know, like if they work in a grocery store or they're a mailman or something like that, there are a lot of people that are still working, you know, and a lot of people are still taking public transportation. And so they're going to be at higher risk, you know. So if you had the demographic profile of individuals like living in some areas, you could maybe refine some of those models of disease transmission by using the demographics. You know, you could even have a like decision to stay home, or decision how many times per month do you leave your house, or, you know, but right now their models, I'm sure, you know, they don't incorporate that because it's mainly epidemiologists, but I could see that economists could probably contribute to improving some of these models over the longer term, you know. Probably there will be research actually using the data from the disease and trying to refine the models. Okay, so the last topic that I wanted to cover in class is non-parametric estimation. Okay, so let me just give you an idea like what it is. So we're going to do two types of estimation. One is density estimation. Okay, and the other is regression estimation. And they're actually big literatures on these topics, and there are many different estimators. Okay, but in terms of what is non-parametric, so remember before we estimated densities, assuming that the density belongs to some parametric family. So when you say like something's normal, you know, with some mean mu and variance sigma squared, that's a parametric assumption. So you can estimate the density. If I estimate mu and sigma, then I have my density, right? So maximum likelihood would give me my density. That's a parametric approach. Okay, a non-parametric approach would estimate the density of X without restricting it to be in a parametric family. Okay, and the reason that might be better is because, you know, suppose I assumed it was normal and it was not normal. So my assumption was incorrect. Okay, so if my assumption is not correct, then, you know, all bets are off, kind of. So, and there are things that don't look normal. For example, wages are not normal. You know, wages, they have like this right skewness, you know. So a lot of times, if you had to use a parametric distribution for wages, people commonly use the Pareto distribution because it can take on that shape. But if you look at like weights of people in the population, like if you just ask people their weight, it's bimodal. And the reason is partly because the men and women tend to have different weights, you know, so. But there are a lot of, can you think of anything else that you're pretty sure is not normal? Test scores tend to be kind of normal, you know, so I would say if a test is well designed, I always kind of look at the distribution if I give a midterm or something. You know, if it ends up bimodal, that's actually kind of bad. You know, like some people understood it very well and other people didn't understand at all. I don't like it if that happens. You know, I try to get it to be more normal. Can you think of any other variables that you think are not normal, probably? And the only thing I know that tends to be normal is like, you know, SAT scores or something like that usually is pretty normal looking. And some things that are not normal, when you take the log, then they look normal. Okay, so some things you can say are log normal instead of, I mean, normality, as you saw, has a lot of convenient properties because we know a lot about these like expressions. You know, normality is easy to work with, but ideally, if we had a method that didn't restrict it to be normal, it would be better, okay? So you'll see that non-parametric density estimation, it's more general than parametric, but at the same time, there are some drawbacks, and the drawbacks are mainly in terms of bigger standard errors. So you can estimate it, but it's less precise. So you usually need pretty big samples, okay? So we'll go into that. Okay, and then regression estimation. How does this work? Well, if we say y equals x beta plus epsilon, we're imposing assumption that E of yi given xi is equal to xi beta. Okay, so that's a parametric restriction. And this actually also affects the derivative of y, because we're assuming that the derivative of E of yi with respect to xi equals beta. So we're really imposing an assumption on the conditional mean and on the derivative, okay? And then non-parametric regression would just say that this is g of xi plus epsilon and not impose assumptions on g. I mean, actually, we will impose some assumptions, but they're going to be pretty mild. Like we'll assume that g has a derivative, okay, and it's continuous. Okay, but that's it. So our estimation method would be valid for any g. Okay, so we don't necessarily have to restrict ourselves to this. And there are tons of different non-parametric methods out there. I'm going to talk about what's called local estimation methods. And they're one of the more popular methods, but I'll just mention some of the others, you know. So, so I'm gonna do, let's see, kernel methods. And kernel methods are local regression methods. I think they're kind of easy to understand relative to some of the other methods, but kernel methods. Okay, but they also have things called spline methods. Okay, spline methods kind of piece together smaller parametric models. So you can probably take courses in the statistics department only in spline modeling. Okay, it's like a competing method for this kernel method. And then there is also like neural network models. There's, let's see, spline models. There's like global polynomial or global like series methods. Let's see, series. And then there's some methods that I just have never even used, but there's like, I don't even know if it's used that much now, but like there's something called wavelets. So there are actually a lot of different methods out there, and we'll just be looking at one of them. But the one we're looking at is one that's used commonly in econometrics. I would say in econometrics, they mainly use kernel models or neural network. In statistics, some people like to use splines. All right, so mainly we'll just look at kernel methods. Okay. All right, so density estimation. So the simplest non-parametric density estimator, I'm sure you've already used, okay? And that's the histogram. You probably did not realize you were using a non-parametric density estimator. Okay. So when you do the histogram, this gives you the fraction of observations that falls within a bin. Okay, and we'll say that the bin starts at x naught and it ends at x naught plus h. So the width of the bin is h. Okay. So with the histogram estimator, if I took the density and multiplied by the width of the bin, you know, because let's say it's some continuous density, this density times the width of the bin should be approximately the fraction of observations that falls within the bin. Okay, so this notation here, let me just explain what it means. This is an indicator function notation. And this means this takes on a value 1 if the variable xi is in this interval. Okay, so that equals 1 if the condition inside is true. Equals 0 otherwise. Okay, so what I'm basically doing is I'm summing up how many observations are in this bin. So how many of the x observations fall in this range, and then dividing by n. So that's just a fraction of the observations in that bin, right? And any questions? Does it make sense? Okay, because this is the motivation for a histogram density estimator. So the density estimator would be f hat of x naught is equal to 1 over nh. So I just moved this h over here. That's it. Okay, and that's the histogram density estimator. I mean, this is really approximately equal to. And we'll look under what conditions this is a consistent estimator. Okay, so we'll look at like so remember for consistency, well, it turns out it's not unbiased. Okay, it's going to be a biased estimator, but under certain conditions, the bias is going to shrink to 0. All right, and we'll formally look at that, but we're going to require that the h has to go to 0 as the sample gets large. Okay, so maybe that's kind of intuitive. I think if you use R to do a histogram, if you have a lot of data, it's going to have more bins. Like it automatically does that, like when you draw the picture. Okay, but there's a reason for it, because the histogram estimator consistency will require that h shrinks to 0 as n gets large. Okay, and so let me just show you the bias. Okay, that's probably all we'll have time for today. But then next class, I'm going to show you the variance, and we'll derive out like the optimal size of h. Okay, let's look at the bias. Okay. So E of f hat of x naught. So it's going to be 1 over nh times, we had a summation, okay, but we're assuming the observations are independent. So this is going to just be times, well, I can write it here. So E of 1 over h, or 1 over nh times the sum. Okay, that's what we're doing. So the 1 over n is going to cancel with the n terms. So we're going to have 1 over h times the integral, writing out what this expectation is. Okay. Now, this is the range of xi. Okay. But this is only going to be 1 in this interval. So I can rewrite this as just taking the integral, because everywhere else it's 0. So I can make this as x naught plus h. Okay. All right, let's see. Question Kai. Let's see. Does this function only take n possible inputs? Actually, which function, Kai? So xi is the data. There's no y. It's only density estimation. Like we just have x. We don't know what the density is. So I'm not going to say it's normal. I mean, it could be normal. But the xi, those are like our data points. And they come from some density, but we don't know what it is. So the only function that we have here, f, this is an estimator. I'm considering this as my estimator of the density. And it's a function of the data and of the point x naught. So x naught is, I choose x naught because oh yeah, you know what I should mention? This is a local estimator. So when I do this, I will get the density value at 1 point. Maybe that's what you're talking about. That I'll only get the density estimator at x naught. So if I want to get a different density value, I could look at a different x naught. Okay. See, would the outputs for any value between x naught and x naught plus h be the same? Well, as I change x naught, I would be changing that interval, you know? So if I change the x naught, then different x's would be within that interval. You know, so therefore I might get different density estimates as I change the x naught points. Because I'm basically adding up all the observations within this interval. You know, so like, let's say I had earnings data and I say, okay, my x naught point is 50,000 and my h might be 5,000. So then I would be looking within this interval. How many people have earnings in the range of 50,000 to 55,000? And then if I change it to be 100,000, you know, then it would be like 100,000 to 105,000. So different numbers of people could be in those different intervals. So I can get different estimates, but it's a point-wise estimator because I'm only estimating density at a point. So when I do the normal distribution and I get a mu and a sigma, that gives me the density at any point. You know, I can derive out the f of x at any point. But here, this is point-wise. Point by point, I'm going to get the density. Okay, so to analyze bias, we take the expectation. Now, at this point, we're trying to estimate f of x naught. So you do a Taylor expansion. That this is f of x naught plus f prime of x bar times xi minus x naught. So it's actually an exact Taylor expansion. Okay. So the first term is going to be f of x naught divided by h times this integral. Okay, and this integrates to h. Okay, so this is going to cancel with this. So that's good because that means that my leading term is f of x naught, and that's what I'm trying to estimate. So that's very good. But the next part, this is the bias. Okay, so this is an example of a bias estimator. Okay. dxi. All right, and this is called a remainder term. And notice that the remainder term is a function of h and x naught. It's not a function of xi because we're actually integrating out over xi, okay? But this is the bias. So this estimator is actually a bias estimator. And what I need to do is I need to study this bias term and analyze the conditions under which the bias will shrink to 0. Okay. Well, since this is an exact Taylor expansion, x bar is between xi and x naught. Okay. All right, so far we showed this is what we're trying to estimate. So the leading term is f of x naught. So if we can get this to go to 0, then we will have shown that it's asymptotically unbiased. Okay, so for consistency, we actually need two conditions. We need that asymptotically it's unbiased, but we also need that the variance has to shrink to 0. Okay, so next time we're actually going to look at the variance and the bias, okay, because you actually need those two pieces. All right, and let me just maybe right quick just say something. We're going to, in analyzing these terms, because it turns out that the main condition required for the bias to shrink to 0 is h has to go to 0. Okay, that's going to be what we show. But we're going to use this notation, which you might have seen. I'm not sure how many of y'all have seen this in other classes. First time I saw it was in a class on algorithms, actually. So if you took a comp sci classes, you might have seen this. So we say xi or xn, we're going to use this little op1. It's big O and little o. I mean, it'll be clear when we use it, I think, how this works. But this is called little o. Normally in computer science, you don't have the P. So the P stands for probability. In comp sci, you normally would just have little o without the P, but we're going to do like order in probability. Okay. So if I say if xn converges in probability to 0, it's little op of 1. And xn is little op of h if xn over h. So h is actually also going to depend on n for us eventually. Yeah. Converges in probability to 0. So if I divide by h, so if I take xn and divide by h, and that converges in probability. So this is the same convergence in probability we had before, then that would be little op of hn. Okay, and then there's one other one. We're just going to use this a little bit, this notation. You say it's big OP of h if xn over hn is stochastically bounded. So it's not going to infinity. Mainly we're going to use the little o notation. Okay, and I noticed there were a couple of typos in here where it should have been, it says it's big O and it should have been little o. So I am going to upload a new version to correct it. Because I noticed a couple of places it was big O and it should be little o. All right, so we're going to, I mean, don't worry about this now, I'm just kind of introducing it because we'll use this next time. So next time we're going to show consistency of the histogram estimator by analyzing the bias and the variance. Oh, just in the last couple of minutes, On the fourth problem set, I asked you to apply, to basically to do the non-parametric density and regression estimation, okay? But, and we're covering the formulas, you know, that underlie those estimators, but I'm not expecting you to program up the formulas. You know, I didn't want to make the fourth problem set super demanding. So you can just use the built-in commands. And I give you the commands in the problem set. Okay, so problem set is going to be mainly to try out these methods and just to see how, like, the estimator, how it's sensitive to the H, like the, you know, the pictures you get. So, you know, once I cover this, even after next class, you should be able to do number 1 on the problem set. Okay. Well, yeah, so we did assume, yeah, Omkar is asking, we did assume it's differentiable. That's correct. Because in order to do the analysis, we assumed it had 1 derivative. Yeah. The other assumption we're going to assume, I haven't done it yet, but we'll assume the derivative is bounded. That's it. So these estimators are consistent under very weak assumptions. So that's the advantage. Actually, I should mention these estimators, they're not just used in economics. They're used, I think, a lot in engineering. Like, I had a friend who's a radiology professor, and he worked a lot on, like, MRI images. And they use these methods to, like, improve the image you would get from, like, a CAT scan or an MRI. You know, so I think there are a lot of engineering applications as well, and they're used all over in statistics. You know, so okay, well, I guess we're out of time today. So if anybody has questions, you know, as you're working on the midterm project, feel free, you know, just drop me a message. I'm happy to meet with you. You know, since I'm stuck at home, my schedule is more open than usual. You know, and then of course we have office hours on Mondays usually, and Gabriel, I think she posted her office hours, so she's also available. Okay, so I hope that you all have a good week, and I'll see you on Thursday. Okay, so bye.